start to stream.
Okay, so is it okay with the screen sharing at this moment?
Yes, it seems so.
You confirm? Yes, okay. So because of some technical issues, I will use this black box here as a pointer. So don't ask any strange questions. I don't know why my cursor cannot be displayed. And just to save some bandwidth, I will also turn off my video. So now I would like to focus. I would just put the focus on the presentation itself, not on myself. Okay, so the topic of this something like an hour-long presentation is that how can we derive accurate photometry on test targets using differential image analysis, which means that in principle we use imaging data, which imaging data is based on basically full frame images, and we try to figure out why it is important to do differential image analysis, what are the bottlenecks, and what are the problems which need to be solved. So there will be a little summary about the mathematical background. I will show you some examples for a particular target. I will in detail a little bit some aspects of the implementation, and of course, if we are talking about things like big data era, I would like to make a kind of insight that how can this huge amount of data be managed easily or more or less easily, or what is the I would say optimal way of handling this type of analysis. So let's start with this. So as I also told you, know that TESS provides various types of data, basically two types of data, and one of the data type is the full frame images. So these are big images, 2K by 2K images per CCD, and we have a time series of these images. And there are basically three directions which can cover our scientific interest regarding to this type of imaging data. So first is the spatial coverage. So what is the field of view of our interest? So because TESS has an enormously large field of view, it covers 7% or nearly 7% of the sky at the same time. So this is a very big. This can be very big, but of course, if we are interested in just one particular star over there, we don't have to do, or we don't have to use all of this data, just we have to extract what is our interest at this moment. Of course, we can have interest in brighter targets. There are just a few brighter targets for TESS. I mean, few, it's an order of thousands, tens of thousands or something, but TESS is also able to look for very faint targets. So is it possible to do photometry on targets which has a magnitude of 18, 19? So it's very, very bright. So there are literally billions of targets at this regime. And of course, we do time series analysis. So we cannot analyze just a single frame, but we have to run through a bunch of frames. And if you remember, 2 days ago, I explained that when we were just talking about the glossary of TESS. So TESS observations are divided into sectors. So in one sector is exactly one sidereal months long, so 27 point something days, depending on the actual perturbations. But while the moon makes one revolution, one orbit around Earth, TESS does two orbits, and during these two orbits, TESS points to the same field of view, and we have a half an hour of cadence, and we divide 1 month with half an hour. We get that the number of the frames in a single run is around 1,000. It can be a little bit higher, it can be a little bit lower, but the average is 1,000 and a few hundred, basically. So there are a lot of frames. And if we are talking about postage stamps, so short cadence data, the number of the frames are multiplied by 15. So it's even more data at the first glance. But considering the spatial coverage, short cadence data is not the same, because only, say, 10 by 10 or 15 by 15 pixel large areas are covered. And of course, or not really, of course, but mainly short cadence data are for brighter targets and not for fainter ones. So I will show you a test case. This is a error layer type variable in one of the southern constellations. It is observed by TESS at the very beginning of the mission, so sectors 1 and 2. And this is a very confused area in the sky. So that's why I picked up this target at this moment, because it's a very, very good example that while the star itself is isolated, if you look through a telescope or make a high resolution image with any kind of ground-based instrument, but with TESS, if the separation between the stars is just less than 1 arc minute, and if the stars, the nearby stars, had nearly the same brightness, it's not so trivial how to do it. And here is that just a few numbers about the stars. This is the GAIA DR2 number. This is the astrometric parameters which are solved, which means that we have a full 5-parameter astrometric solution for the star, which means that the observation by GAIA is very good. So we can also rely on the photometry, and the photometry says that the R band magnitude of the star is 14.2, which means that it can be used as a kind of TESS magnitude. And it is, if you look at in TIC, the TESS input catalog, it is just between 0.015 sigma from this magnitude. So GAIA DR2 is a really good start to estimate TESS magnitudes at the first glance. And of course, as I told you 2 days ago, there are many other type of effects, not just confusion, not just confusion of nearby stars, not just so this means that the nearby sources are overlapping, but there is stray light, significant amount, and there is something which is called differential velocity aberration. I will talk a little bit later on, because it's a very interesting effect, and TESS was the first instrument ever built by mankind that faced with this problem in a quite significant way. So differential velocity aberration, something which need to be analyzed, and these problems should be resolved. So I will show you the examples later. Okay, so this is a normal sky image taken from the digitized sky survey. So from the southern part, I think it's not called Palomar Sky Survey because it's conducted from the southern hemisphere, but yeah, so this is the target star here at the center. So I'm just pointing with this black box with the upper left corner. So this is the star, and there are nearby stars here, here, and here, which are pretty close. So the distance between two stars is less than 1 arc minute, which means that if we look at the same image with TESS, we can clearly identify those stars. And instead of this 1, 2, 3, 4, 5, 6, 7 stars, separate stars, we see just a kind of bunch of pixels here. So we cannot really see our target. It's not separated from the nearby stars. It's just a messy, a confused area on the sky if you look with TESS. So the goal is to extract some sort of photometry with TESS, which is using this these series of images and focusing in this particular star, which is, well, it cannot be seen as a star on TESS images, but it's a kind of kind of bunch of pixels, just we are interested in. But the good thing is that if we just take a few subsequent frames and we just subtract it, we clearly see the variability. So this is the variability of the star. This is really at the center of the image. So we can conclude that, okay, this star is really doing something, which is good. And we can see the residual, which is basically noise, which is background noise or readout noise or some sort of noise. And we see also some leftovers just at the position of the very, very bright stars. So if you just jump between the images, we see that this one, these stars over here are very bright. It's order of 8, 9, 10 magnitudes. It's also very prominent, these stars on test images. And of course, on differential images, there are some residual because of the photon noise of the image. So as you can see, this is the photon noise. Here is readout noise. And what is good that our variability of interest is a well-isolated signal. So regardless of this mess of pixels here, we can clearly separate the variability of the star, which is good. So let's watch the movie. How would this star look like? So this is a movie. As you can see that something is going on here. It's pulsating. You see that there is a little variability in this corner over there. I don't want to hide it, but yeah. And as you can see, there are some strange artifacts. There are these vertical straps here. These are very faint. So at first glance, you would see that you don't need to care with this because they are far away. You don't really know what it is. So this is the variability on the original images. So if you just open any data retrieval tool with TESS, which are like the mass portal, you can download images like this one. You make the trimming of the images, you make the alignment of the images, and you will get something like this. So let's check the difference. The difference will look like something like this. So the star is pulsating at the center. So the pulsation is not so clear in the shared animation, but Marek was able to share the presentation itself, and you can open it. It's an ODP presentation. Then there are some embedded GIF images which shows this variability. So as you can see, the variability is clear at the very center. It's much more prominent. But there are also other kind of artifacts that you can see on the images, like the residual image of the stars are not pure photon noise, but it's a kind of interesting structure which can be characterized as a kind of difference of two stars which are not at the same position, which means that there is a shift in the images, a gradual positioning error or something like that. And you can also see that this very, very bright, not so very, very bright, but now these straps here are even more prominent as in the first series of images. So we have to figure out what's going on here, because now the variability is much more clear. So we hope that good photometries can be done using this target. But we have to get rid of this everything else here, because this affects our photometry. It's not good at all. So we have to figure out what's going on. So I will talk a little bit later about the root cause of this effect. But if we perform image convolution at the same time, we can get rid almost all of this side effect of the positioning error. We will see that it's not literally an error. It's an effect of this aforementioned differential velocity aberration. And if we get rid of this effect at some level, we can clearly see that the residuals are much more smaller. The variability is even more prominent. And not just the variability is more prominent, but these vertical straps are also very, very strong at this moment. So if we wait a little bit, there are phases when the stray light is stronger. So the moon and the Earth was closer to the optical axis of the cameras, which could yield such a prominent features of the image, but these are images not good. So we just have to deal with it and remove it as soon as possible. So if we go on and we make a kind of median filtering, which median filtering is now done in vertical blocks. So we just simply compute the median of each column, and this median is subtracted, then we can easily remove these straps. So it's a very easy process, very quick. It can be done in parallel with the photometry, so you don't even have to save the images in real applications. But now you can see that it's perfectly disappeared, and you can also see that there are some other features. For instance, this one. This is also a variable star over there, and it was hidden by these vertical straps. So now we were quite lucky that this target of ours is not affected by these vertical straps, but some of the other targets were not so lucky in this sense, and they were just hidden under these vertical columns. One of the first supernovae analyzed by TESS was also affected by such artifacts, these vertical columns. These vertical columns are also very interesting. These are kind of technological side effect of the CCD manufacturing process. So these are reflection of some particular gates, electronic gates underneath the CCD, and these gates are more reflective in I wouldn't say far infrared. It's not far infrared, but the longer wavelengths at test band. So they reflect more light in 90, 900 or 950 nanometers, which means that these traps can appear when there is some stray light. So basically, it's also earth shine, but it's amplified by the detector a little bit. So it's a kind of side effect of the manufacturing process of the CCD, which has some, of course, many advantages, because the gain is very high, the charge transfer efficiency is very close to unity, so the CCDs are very good at the cost of these vertical straps. And of course, the photometry can be done, and if we do it, then we get a very nice light curve, and this is good. So this light curve itself is ready now for scientific analysis. So let's discuss a little bit about the mathematical background of this type of image processing. Why it is important? Because as we see a few minutes before, if you just simply subtract two images, the result is very nasty. It's not optimal. Even with text, even with very good pointing, it's not so optimal. So we just have to transform one image to the references or to the other image just to correct for this very small, apparently very small, but if you just consider differences, it can be very high effects. So it's basically, the question is, how can it be done? So basically we have an image, this eye, and we have a reference image, and we just want to compute the difference. If you just subtract this quantity, the image, from the reference image, we will get nasty results or nasty frames, like, just a minute. Oh, sorry, it's a little bit slowish. Sorry, something is went wrong. Just a moment. Oh, sorry. Just a moment. I'm just restarting this presentation. Let's hope that's going to be okay. Okay. Yeah. So I just wanted to show this slide again, where we just simply subtract two images. So this is bad compared to the most ideal case. This is this one, or close to the ideal. So we are just interested now in the mathematical background of this process. So the first thing what needs to be done is there can be a shift in the background level. So background always is something which is always changing because of the changing of gradual changing the electronics, the readout process, the bias level, and in the case of TESS, also the stray light is prominent, and also the background can be not homogeneous. So there is a way how to handle it if you model it as a kind of spatially varying function, like a linear slope or linear gradient or something like that. But you can also apply higher order polynomials. It depends on the field of view. If you have a smaller field of view, like a few arc minutes, it's probably fine if you model it just with a constant number like b0, this one. But if you have a larger field of view, say 1 by 1 degree, something like that, then it's probably better to model it by a simple linear function. If you have a very big background, which means that it's 24 by 24 degrees, like the full field of view of a test camera, or 12 by 12 degrees, which is the largest continuous frame that can be retrieved with TESS, is 1/4 of the field of view, which is the field of view corresponding to 1 CCD. Then you would better to use a kind of spline function. So all of these are fine. It depends on your field of view and depends on the amount of stray light. If the stray light is smaller, then you can just go with smaller amount of unknowns or quantities in this function. So this is the B part. And what is K? So K is something which can account for the shift in the images, if there is a tiny difference, order of a few hundredths of a pixel or a few tenths of a pixel, and if there is some sort of variations in the profiles because of defocusing or changes in the focus or something similar, or because of the temperature of the whole system varies as it orbits Earth, then it can result in different profiles for the stars. And if you make a simple convolution, then we can just do it. So what does convolution mean? Convolution means that we have a image, we just convolve it with this operator denoted by a star or asterisk, which is a blurred something, and we get a blurred image. And the question is that we have to apply this function, we have to do the convolution, add some background variation, and then we minimize this difference. And if we can minimize the difference, then we are able to retrieve what is the difference, real difference in the background, and what is the real difference in the variation of the profiles using this type of analysis. And the good thing is that there are many processes in the data acquisition of a CCD camera, which are said to be a kind of linear process in terms of convolution. So we have two images, F and G. We apply a convolution transformation. Then we can say that if lambda and mu are constants, like real numbers, then we can just make this rearrangement with the convolution. So first we do the convolution and we multiply with these constants and we add back, and then it yields exactly the same, results in exactly the same image when we apply this linear transformation and then do the convolution. Which means that there are many physical effects which is linear and can satisfy this. For instance, smear, spacecraft jitter, and even the momentum with the saturation, if it is very small. We can also model the focus changes in the PSF, point spread function, and we can also correct for stray light or zodiac light if there is a smooth variation in background. So a lot of effects which affect the data acquisition of tests can be corrected by this function, which is good. For instance, jitter is uncertainty in the pointing, basically. It's called jitter. It's measured in the units of arc seconds or sub-arc seconds or pixels. So the good thing about linearity is that we can model this type of effects in arbitrary order. So if there is an image, we need to apply the convolution transformation. It's independent whether we apply a kind of jitter correction and the straight light correction, or apply the jitter correction, straight light correction, and then we do the convolution. So this is a good thing about the linearity, which means that the order, how would we model it, how would we do it, is somehow irrelevant. So it can be done, it can be implemented, and it's because it's a linear fit. So if you have a bunch of points and you just want to fit a straight line to the point, it's exactly the same complexity in terms of mathematics, but the number of parameters which should be taken into account is large. For instance, if you have a 2K by a 2K CC, then you really need to apply these equations and this type of formulae for literally 4 million points. But there are many other effects which can be found on test CCDs, which cannot be considered a kind of linear process in this way and cannot be modeled. One of the most prominent effects is saturation, blooming, and these vertical straps, because these vertical straps are also somehow a kind of nonlinear response. Why it is interesting, why it is important to do it. So saturation and blooming, these two are related, of course, because if we have a saturated star, which means that the ADCs, the analog digital converters in the CCDs could reach their maximum. This is one type of saturation when there is some sort of information loss because these type of electronics cannot provide numbers higher than a certain value, or the full well capacity of the CCD pixels is smaller than the total amount of charge which are inducted by the photons coming from the stars, then saturation would occur. So TESS electronics is set up in a way that saturation wouldn't yield charge loss. So this is good, which means that you are able to count all of the photons, just you have to look on the nearby pixels as well, and not just on the target pixel. Which means, and this effect is called blooming, so if you see a bright star and there is a vertical strap emerging from the star, going up and down, this effect is called blooming, which is not a big problem in the case when you're able to count the photons, but the unfortunate thing that you cannot really apply this type of differential image analysis. But there is a good thing that differential image analysis are basically good for faint stars. I've shown you this example with some random pulsating star in the southern hemisphere. It was 14.2 magnitude. But blooming starts at 5, 6 magnitudes, depending on the position of the image on test stars, which means that there is a almost, I don't know, 6, 7, 8, 9, 10 magnitude difference with our target of interest, where we can apply this differential image analysis, and the region when the saturation and blooming occur. So this is good. The only problem is there when the saturation or blooming affects our fainter stars in terms of overlapping, but this is not so frequent. It's a little bit rare effect. So of course we should get rid of these pixels where this type of accretion is not true anymore. So it should be masked at some level, and if it is masked, then we can just proceed with the normal way as we do. And as I also mentioned, these vertical straps can also be removed with median filtering. And median filter is a very nice process. It's very simple to do. It's very simply implemented. You can do it with your favorite tool anytime. It's no problem with that. The problem here is it's not a linear process. Because if you have a bunch of numbers and if you have two images, you add the two images and you want to compute some sort of median statistics, it won't be the sum of the median of the corresponding statistics on the individual images. So it's not a linear process, which means that you can apply in conjunction with these convolution-based transformations. So let's talk a little bit about the aberration. So we all know this type of aberration when we are walking in or running in rain or driving in rain. And exactly the same effect can be observed if someone uses a telescope. Because of the Earth orbits the Sun, there can be a slight difference at the order of 20 arcseconds because of the motion of the star. So if you compute that the orbital velocity of Earth around the Sun is exactly 10 to the minus fourth of the speed of the light, it means that there will be an aberration, a difference in the position of the apparent location of the stars, which is exactly in the same order. So 10 to the minus 4 power of radians. And if you convert 10 to the minus 4 radians into arcseconds, you get 20 arcseconds. And 20 arcseconds is exactly one test pixel. So it means that if you look on a test image, you can say, or you can see that the stars can be away from their ideal or intended position by 1 pixel. This is good, because if Earth wouldn't, so if you just take a few images, then in all of these subsequent images, the stars are nearly at the same position. But the problem here is that during this 1 month campaign, what TESS has, the difference can be higher. So let's make it clear a little bit. So this plot here shows the field of view of TESS. So these are 4 cameras. This camera faces towards the ecliptic or close to the ecliptic. So ecliptic plane is somewhere over here, like this. And this is the ecliptic pole at camera 4. And this is the difference between the position of the stars with respect to the frame acquired at the middle of the campaign. So we can just see what is the apparent movement. Of course, it's extragated. This effect is extragated here, but because of these identities here, that one, if we define this as field of view of TESS, which is 24 by 24 degrees, it's roughly the same when you just consider numbers, that 1 TESS pixel is around 21 by 21 arc seconds. Which means that if we divided this square into smaller cells using this grid, then we can say that one grid is 1 by 1 degree if we consider it's a kind of part of the field of view, or it is 1 arcsecond if we refer this block as a kind of test pixel, and we just want to show that what is the difference of the apparent position of the stars here. Which means that, as you can see at the beginning of the sector, day 1, the difference is at the order of 3, 4 arc seconds, which is roughly 1/5 of a pixel. Here, there is also a non-negligible difference, which is an order of 1 arc second. And if you go on, let's say day 8, the difference is smaller. At the beginning, or sorry, at the center of the bit time of the observation is negligible, and then it goes to the other direction. So as you can just see, the position of the stars at the beginning of the sector and the end of the sector can be, well, it's not as big as half of a pixel, but it's larger than 1/4 of a pixel. So this is something which was not, well, it was known. I mean, you can compute using the appropriate formula that what is this difference, but it was not a kind of prominent effect until TESS. So this is why it is important to not to do naively this type of differential image analysis, because these images are affected by artifacts like this one. Okay, so this series of images, I hope that it's clear, or more or less clear. And the interesting thing with this is that if you just look on normal test imaging, if you just download something and you just open it with DS9 or any kind of favorite plotting tool or something, you cannot really see because these are very, very small differences. But if you want to do more accurate analysis, more accurate photometry on images, you cannot neglect these effects. And the problem here is that if you have some sort of long-term variability in your star, like if you want to do accurate photometry for 1 month long period, or 2 orbits or 2 sectors, or even if your star is here at the ecliptic pole where you need to, or you can observe for nearly a year, then you still need to solve this type of problems, because otherwise your photometry wouldn't be accurate. And if you just do naively the photometry, this type of these effects or artifacts could yield false variations. False means that false means that sorry for the interruption. I'm just yeah, it's okay, it's working. Okay, sorry. Okay. So let's start again. Sorry. So if you neglect all of these effects, you can get similar type of variation, but could mimic astrophysical variations. So this is the problem. So the timescale of these variations are comparable to the orbital period of TESS, or something similar. So if you detect a variation which has a periodicity of 13.7 days or 27 point something days, then you can think that it's probably not physical. It's probably due to some observational artifact because of effects like these uncorrected differential aberrations. Okay, so I would like to show you some numbers in terms of analysis resources, that what kind of computing and storage capacity is needed if you want to do this type of analysis. So these are kind of, I would say, it's a massive analysis. If you want to do the whole process for the whole series of images, and you want to process in a way that sector by sector analysis. So these processes need I would say, lots of resources, but these resources are not considered as a kind of very big amount of storage space or memory in terms of modern standards. So if you say that, okay, we have to retrieve 1 terabytes of data per month, at first glance it sounds big, but if you can buy a hard drive with 10 terabytes of capacity for a few hundred of euros, then it's not so big. So what we do, or what can we do at the first glance, is just to mirror everything from the TESS bulk download website, and then we start the process. So what we do, and what you can also try later on, hopefully, is that having this type of archive and mirror, which is somehow pre-processed in a way that you don't have to deal with astrometric solutions, you don't have to do with source identifications, because all of these preliminary data processing steps can be done in advance. Then you can do the per target processing quite quickly, and even since these numbers are derived, this photometry of one sector data can be done within a few seconds, running on a few, like a dozen of threads on a normal computer. What is a little bit slower is the extraction. So if you're interested in just in a single target, then you need to extract from the full frame images, and it might take a little bit longer, and not just because of the amount. Well, because of if you want to extract this amount of data, you basically need to check not all of the images, but all of the images from a single camera from a single sector, which is in the order of, I would say, 40, 50 gigabytes. So you have to pick up 40 gigabytes, you extract your favorite star or favorite field of view, and then you can do the processing afterwards. So yes, yes. So how can we continue? Just a moment. Okay, so I am just showing some screenshot of this pipeline, which is a particular implementation based on a FitSAs package using these utilities to perform this type of analysis. And as you can see here, this can be done within a few seconds, so 3, 4, 5 seconds, depending on the target. And in total, because of the parallel processing, it needs a little. So the total time which is used by the CPUs participating in this process is a little bit longer, which means that you can run this script. You have to define the sector number, you have to define the target coordinates, and you have to define the reference magnitude for this particular object of interest. And of course, the coordinates are needed just to center your aperture, your photometric targets. And the reference magnitude is an interesting thing, because if you have a variable star and you have basically nothing but differences, and you conduct the photometry on the different images, then you certainly, or you really need to have some hint for 0-point magnitude. Okay, it's a differential flux, it's a differential magnitude, but what is the 0 point? What is the reference magnitude? And if you have a very confused field, it's very hard to obtain it. It's very hard to extract it using very big pixels like what TESS has. So that's why it's very useful to have catalogs like GAIA or GAIA DR2, because GAIA DR2 has a very accurate photometry in the exactly same passband, which means that if you start with it as a hint, like 11.3 something magnitude for this particular star at this particular position, then you can just proceed and continue. And with this, you can also get very nice variations and very nice light curves, something like this. And as you can see, the amplitude here is much more smaller. It's in the order of 0.02 magnitude. So that's why TESS is useful. It's, of course, among many scientific projects, it is very useful for detecting transits, so transiting exosolar planets, because if you do this photometry properly, then the small differences can easily be detected. So this is the target of variability, the star at the center. So I just show this light curve of this target from sector 7. So this is, as you can see here, the light curve of all of the test targets from a given sector are built up from two parts. This is the first orbit during the observation round. This is the second orbit, and this is the gap when TESS was the closest to the Earth. And this gap, during this gap, which is approximately 1 day long, TESS performed the data downlink towards Earth, which means that the satellite should point its high gain antenna towards Earth, which means that there is no data collection at that time. So that's why there is a gap. And after that, when the downlink is done, TESS should point to its nominal field of view. And because of this pointing of the satellite, so changing in its attitude, would result in different temperature distributions in the detectors. There is also additional reserve of few hours until the thermal equilibrium is reached, which also minimizes the side effects of the variation in instrumental characteristics. So this is also an image from the star. These images show that in some cases, stars can be at the very edge of the CCD. Of course, in this case, you are not so lucky because photometry cannot be done if the stars is at these particular positions. But normally, when star is in the center of the field of view, then everything is okay. So as you can see, the field of view is the same. So you can identify the small constellation here. But target star is very clear in this right image, but it's not so clear on the left image. And the interesting thing is that in the case of this type of targets, that if you don't use differential image analysis, even then with just normal photon counting, you can still have some sort of photometry on this type of stars. The problem also with this differential image analysis, that you really need to have some sort of space around your target. So that's why differential photometry cannot really be done in this case on the right. Okay, so I just make a quick summary that this type of analysis methods, how can we use this in practice. So first of all, we have to download everything, which means a lot of effort, but if it is done in advance, then you can proceed. The important thing is here, so just a moment. So you clearly need to use other catalogs for deriving the 0-point magnitude. And one of the best is GAIA DR2, but of course, TIC, the test input catalog, can also be used. So before GAIA DR2, the TIC test input catalog was also established, but in that case, the magnitude levels or magnitude estimation were not as accurate, because originally the test input catalog magnitudes based on various other catalogs, which means that that it's a kind of inhomogeneous data sets. Okay, so target processing is done as I showed you earlier. So if you have a smaller field of view for your target, like 32 by 32 pixels or 16 by 16 pixels, the number of stars in the background or in the vicinity is not sufficient to derive the differences between the images accurately. But if your field of view is higher, like 200 by 200 or 300 by 300 pixels, then the larger spatial variations could also distort your photometry, which means that there is a kind of optimal size, which we found that it's around 60 by 60 pixels or something similar. Yes, so this is also a kind of hint that if you want to do differential image analysis, then you can do it on very small images, but basically you can do on larger images, but then you have to be very, very cautious. But if you don't want to care about anything, then just start with something like 60 by 60 or something like that. Okay. Okay, and just at the end, it's also important to check whether the background variations are modeled properly, because in some cases it might be better to use higher order polynomials or spline modeling, and it all depends on your amount of stray light what you have on test images. So we found that it's interesting because in year one when TESS observed the southern hemisphere, it was the amount of stray light was significantly smaller than in the second year. So it's turned out that for the second year observations, which included the original Kepler field, so there was a very, very high scientific interest of the second year because of the overlapping of the original Kepler field in between Cygnus and Lyrae and such constellations. Because of this, which is good, but the amount of stray light was significantly higher. So we found that all of the algorithms can be used. Okay, so there's no problem with that, but you really need to check how does these differential images look like. So this is a kind of screenshot of this configuration, which tells you that what kind of parameters need to be adjusted. So for instance, if you have a field identifier, you have a target on this field, you use a series of images for reference, which is used to build up that image AR, what I was just talking a little bit earlier about. You can also define the aperture size, and you can also perform this unstrapping to remove these vertical straps. It can be done. It's a simple median filtering, so it's nothing fancy. And you can also have an optimal image size, which you can also define. And during these runs, you can also do some sort of optimization on the kernel normalization. It's also a kind of side effect. So imagine that you have a very bright star, which you want to do photometry, but all of the nearby stars are faint. And if your star is variable, it's a variable star, because that's why you want to do the photometry, because it's variable, but all of the nearby stars are faint, then the difference between the two images will be dominated by the variable star because of its brightness. And if this star is very, very bright, then the variation will also cancel because the merit function is something like the difference between the two images, and this difference will be the smallest when the variability itself is transformed out. So this is a kind of paradox, and you can also help to resolve this issue by increasing the image size, or during the image subtraction, you normalize your kernel function, which is used for the image convolution, to unity. And if it is done, then it's okay. But by default, this feature is not turned on, or it's not recommended to turn on unless you have some sort of very special case. So here are also some examples what can be done with such a kind of differential image analysis. These are classical pulsating variables. So yes, what can be said is a very good photometry. That would be great, but we didn't have the time at this moment to do detailed comparison with normal photon counting photometry and this type of differential photometry, but many colleagues of mine did it, and it turns out that this differential analysis really helped. The only thing that you really have to consider is the 0 point. So this is very important to set it properly. So just some slides of the stars. Of course, there are still some instrumental artifacts. For instance, this part here in the light curve, it's not physical, likely, and also this part is something which cannot be physical. It looks like something nasty. And then, if in that case, you can look on the images and you can have a hint that what kind of problems are there. Okay, so this is some summary. This is just a short summary about this type of methods. And just to make a kind of conclusion, it can be an interesting alternative to other tools. And of course, it's also true that in any kind of analysis, the more versatile tool set you have, the more accurate your results are, basically. So it is always worth to do comparisons with other type of methods, not just differential image analysis, but simple photon counting or simple detrending, because algorithms doing with simple photon counting always perform this type of correction for differential velocity aberration, background variation, and stray light correction in a way that they derive the differences between the ideal results using stars which are not variables, or expecting that if some sort of variability is similar in all of the stars in your field of view, then it's probably an instrumental effect. So this can also be a hint. But the good thing is that about differential image analysis, if you do it precisely, you don't have to care about this, because in that case, your analysis your analysis algorithm will automatically resolve these issues. So that's why I just wanted to make it a little bit more detailed in terms of algorithms and background and mathematics, because if you do just simple photon counting, then this type of details are not known or not really taken into account by the algorithms. So I think that's all. So I hope that this broadcast or something worked. So if you can say something, then that would be great.
Thank you, András, for your talk. It was a very nice insight into the methods and how the data are processed and what troubles we can we can face. So, are there any questions now?
I had a question, András.
Yes.
How do we select the reference image?
Reference image is a very good question. Reference image. Reference images are always images where there is no stray light, and in some sense it's at the middle of the observations. So that would be the ideal, because if you pick up your reference image from the center or the mid-time of the observations, then you can minimize these differential velocity aberrations.
So our references can be, averaged and then used as a reference?
Yes, that's it. So usually the number of references order of something like 10, 9, 11, something like this, because if you make it a little bit longer, then you may lose information in that sense that because of this gradual movement of the images, your point spread functions on the reference images wouldn't be so sharp, which means that you cannot use it as reference images. But if you pick up smaller amount of reference images, it will be too noisy, of course. So one image is not sufficient. If you have 3 or 5, it is not good, but better than 1, of course. But if you have something like 9, 10, 15, this is the most ideal. This is the most ideal for tests. And you also have to consider, select frames which were taken at the time when both the Earth and the Moon was below the horizon of TESS. Because if you ensure that TESS looks like something like this, so the 4 cameras look in this way, 4 cameras, this is the sun shield of TESS in this way, and if you ensure that both the Earth and the Moon is below this level, so below the horizon of TESS, basically, so this is the pointing of TESS, so it's just 90 degrees away from the nominal pointing, then you can be sure that there is no stray light at all. And it's very interesting that it was very easy to pick up such frames in the first year. In the second year, in one of the sectors 25, 26, 24, so the latest sectors basically, there were just a few frames which satisfied this condition. It's very interesting that you had 1,000 frames, so basically 1 month long of observation, 1 month duration of observations, but you were able just to pick up just a few frames which satisfy this condition, because of the huge amount of stray light, which means that the Earth and the Moon were always above the horizon of TESS, so that was a big problem.
But how do you statistically check if the combined image or anything is a good reference?
Statistically,
do we check the PSF or something like that?
Basically, what you can do if you are interested in about the stability of not stability but the robustness of the process, then you can pick up another set of reference images and you rerun the same process, and if you get roughly the same results within accuracy, so you can derive the light curves using both set of reference images, you subtract the 2 light curves in a point-by-point manner, and you compute the difference. And you can also always compute the difference with respect. You can always compare the difference with respect to the uncertainty estimations. And uncertainty estimations based on the background noise and the photon noise. And if it turns out that this difference is significantly smaller, like 0.1 sigma or 0.01 sigma, so it can be very, very small, then you can say that, okay, the selection of the reference images were good.
Okay, thanks.
Okay, any other questions, comments? András, you perform the data reduction with your custom-made software package. I noticed there FitSH and,
yes.
And these things. Is there any tutorial, some documentation to that where this can be found?
Yes, there is a wiki site on the FitSH website where I try to collect some examples and some introductory material.
Okay, I just googled it and it's easy to find. Okay.
If you just open the website, then there is a link for wiki and this. There are, yeah.
Yeah. Okay.
Yeah, it works at this moment. So.
Are there other publicly available software tools for getting the data from TESS and getting light curves from TESS? I mean, I think Eleanor is working.
Yes, all of the other tools are based on photon counting. So there are many tools, the mass tools, basically based on photon counting methods. So that's why I wanted to put some focus on the differential image analysis because it's not well known. And people just ask me quite frequently that what to do because their photon counting photometry is not satisfactory. And then you can try differential images, differential image analysis, and in most of the cases it helps. So in most of the cases better, but because photon counting is a method which is derived from the classical way of doing Kepler photometry. And when you do Kepler photometry, you just pick up a bunch of pixels and you just add up flux and subtract some sort of background, and that's it. And you rely on, in this type of photon counting method, always rely on the stability of the instrument. Because if your instrument is stable, perfectly stable, then this method is very accurate. And all of the TESS utilities basically inherited this way of handling space photometry. What people did with Kepler. And the good thing about Kepler is that the field of view is smaller, which means that the differential velocity aberration was not a significant effect. And also the confusion was not so high, because the pixel size was smaller. It was not 20 by 20 arc seconds, but 44 by 4 arc seconds, which means that the nearby stars, even close to the Milky Way, like in the background, these stars were separated. But in the case of TESS, it's not true anymore, because the TESS pixels are quite big. So 5 by 5 Kepler pixels are equivalent to 1 TESS pixel. So even if you are able to resolve Kepler pixels, it can be a complete mess in TESS. But on the other hand, you can just cover the full sky, not the full sky, but 7% of the sky at the same time. So of course there are many gains of this at the cost of this type of confusion.
Okay, thanks.
Can I ask a question?
Yes, go on.
It's about this convolution kernel. So after we find convolution kernel, we have to do deconvolution with our image E, right?
No, because finding the convolution kernel is a linear fit. It's a linear process. You have to, because basically your convolution kernel is nothing but a 3 by 3 or 5 by 5 pixel map. Okay, there are 9 or 25 unknowns in this equation. If you just compute the convolution in a way that, how should it be done? You derive these quantities and you are all set. It's okay. But when you do the image subtraction, you apply this transformation to your reference images, or reference image, and subtract it from your target image. And you do the photometry on the residuals. So you don't do deconvolution. It's not a kind of, okay, I have a blurred image and let's make it sharper problem. It's a kind of derivation of the photometry, because you are interested in just the photometry and you don't want to know how would your target image look like in a kind of ideal case when there were no other effects. You don't care about this. You care only about the photometry. So you don't do deconvolution, you do just pure convolution on the reference image, and you subtract the two. And you do the photometry on the residuals. And that's it. So that's why this method is very fast compared to your expectations, because deconvolution is something which is thought to be slow process. I think about image processing when people just try to derive some details on blurred images. So it's not that one. You always have a good image, which can be used as a reference, and you try to minimize the transformation, or try to derive the transformation, just minimize the difference between your reference image and your target image. So that's why it's a little bit, I would say, tricky, because you don't do deconvolution. But everything can be done in the formalism of pure linear analysis.
Okay, thank you.
Okay, are there any other questions? András,
Yes?
is there a chance that you could, just in a few minutes, make a short tutorial how you use FitSH and the other things? Just
Yes. So I think both you and Christian have logged into that machine where we just store all of the data.
Yeah,
which is a kind of new.
I just mean if you are able now just to make a very short demonstration, I don't know, producing some light curve, very quick.
Okay, let's try to do it. Do you have a kind of, I would say, favorite style or some preferred target or something what we can use for kind of demonstration?
I think that the binary group works on AI Phoenici.
So again, please, AI
PHE
Phoenici.
Phoenix. Is it correct? Is there anyone from the binary group?
It's correct.
Oh yeah, okay, so it was observed, just a moment, just trying to figure out, AIPHE, right?
Yes.
I put it in the chat if you want to check.
Chat, just a moment, how do I check the chat? Chat.
It's on the bottom toolbar.
More, chat, yeah. There is nothing in the chat.
Sorry, it was to the waiting room. Sorry.
Yeah, okay, so it was observed in sector 2, right?
I don't know, actually.
Yes, correct.
Okay, so this target, do you know the GAIA magnitude of this target as a kind of 0 point? Anyone?
8.4207.
Because if you just let me. I will share the screen of mine again, and then let's check it. Okay, so waiting. Just a moment. I'm trying to. Okay. So switching off the video again, and then start to share the screen. That's it. Perfect. Okay. So if we go to Simbad something, we look for the star is PAIPAG. That's it?
Yes.
Okay, perfect. This is a binary, yes. So this is the GAIA DR2 ID, which is good. And if we are lucky enough, then we can just figure out the GAIA RP magnitude. But let's do it this way. Oh, sorry. Yes, so the RP mag is 7.912. Yes, because the GAIA magnitude, the G magnitude is 8.42. Okay, but this is the magnitude, this RP magnitude, which is the closest to the test passband. So we have to use this one at this moment. So let's have the coordinates of the start. Coordinates this one. Okay. So let's retrieve it, which is something like we extract from sector 2. We define the coordinates. What was that? Sorry. Okay. And we have the reference magnitude of 7.912. Okay, and we name it AIEAE. Okay. Okay, so the extraction is done. And we run all of the scripts. Now it's performing the convolution and the differential analysis and so, and the light curve is done. And then we just need to plot it. Yeah, that's it. So this is the eclipse, I would say.
Mm-hmm.
This is very small, right? Is it true? The depth is very small. It's 1/1000th of a magnitude.
I don't know. Can somebody from the binary group comment on that? No one.
Okay, probably we get rid of the bad points quickly. Oh, sorry. Yes, it has some stray light at the beginning of the sector, which is clear. But I think the signal is here, so I think it's good. I don't know whether it's astrophysically correct or not.
Yeah, it seems reasonable.
And this is also seems to be a kind of eclipse. But of course, if you want to do a more detailed analysis, you may want to look on the images. Probably the images looks bad because of some instrumental effects. So let me just copy this here and do some. Just a moment.
And so these scripts you showed in a few minutes ago, they use FITES and the PECSEC and these tools, correct?
Yes.
So everyone can write
yes,
their
yes.
own scripts. Okay.
Yes, yes. So these are the differential images. Oh, it looks bad. Let me show the original ones. Oh yeah, because it's too bright. Yes. Yes, yes, it's too bright. Yeah, so this might be a good example when you get rid of the when you need to apply this normalization function. Yes, okay, I understand. So just scan this through, and then you retry this again.
And then it will also become deeper, right?
Sorry?
Then it will also become deeper.
Yes, 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 yes. Okay, yeah, because it over dominated. It's over dominated the field of view. Yeah.
Yep.
Oh. Yes, now it's better. Yeah, it's a too. I think it's maybe the target itself is too bright, and also there is a chance that it might be saturated because it's too bright. But we have to check it carefully. Yes. So basically, this method was designed for, but the use case is basically for faint targets. And if it's something is too bright, then it's probably you need more fine tuning. We don't really apply this type of analysis for such a bright target. So in that case, probably naive photon counting can be, I wouldn't say it's better, but it's more accurate. If you want to do fainter targets, then differential image analysis methods are more accurate than compared to photon counting method. So what I showed you in the example at the beginning with the 14th magnitude of star, you cannot do basically anything with simple photon counting. So this is a kind of drawback. So probably the star itself is too bright because it over dominates the field of view. Yes. I'm just trying to figure out whether it's saturated or not. Probably it's not saturated. Yes, so saturation cannot I think it's not an issue for this. But yeah, brightness can be a problem.
I mean, another question. In the morning, for example, I was playing around with the light group of Beta Umi, and I wanted to download the FITS file, and the size was 5 gigabytes for one FITS. Can it also that it's completely saturated then?
So 1 gigabyte for one FITS file?
5 gigabytes for one FITS file.
5 gigabytes. So is it the time series?
Yes, but for one test sector only.
So one test sector, 5 gigabytes, is short cadence data?
Yeah.
Oh, then it's reasonable. Yes. But it's a kind of did you analyze the target pixel file or the light curve file?
I wanted to analyze the light curve file, but I stopped because I had a memory problem.
Yeah, it's a good question because if you have a target pixel file, which means that you need to store something like 10 by 10 pixels or something, your number of frames within a sector is around 220,000. If you sum up, then yeah, you can easily get up with such a big files. Yes. Yes, but it's a cost of. I mean, it's not a cost. It's a kind of is the result of the short cadence. data and not the. So is there any short cadence data for this particular target, you mean?
I thought, but maybe I was wrong. Maybe I mixed it up.
Otherwise, it's not so easy to produce 5 gigabytes of data for a single target, or in a single hits file, I mean.
Yeah.
Because test frames, normal test frames with FFI data for a single image is just 32 megabytes. So it's small. It's much more smaller.
No, there are short cadences. Yes.
Okay. Yeah, so this star probably is too bright. I mean, it can be tuned. It can be tuned, of course. So there is another way to do photometry on such a faint star using differential analysis. You just simply, if you when you derive the convolution transformation, you put a mask on the star itself, which means that it will have no effect on the derivation of this convolution transformation, which means that regardless to its brightness, it will be based on the nearby stars, just on the nearby stars. So this is something which we need to implement because it's a very, very rare case when we want to do differential analysis on such bright stars. I can basically check later on, probably tomorrow or something, and I can send you some results or some scripts based on this. But actually, yeah, so the use case is a little bit different.
So what is the magnitude limits for the differential analysis?
Yeah, it's we were able to do photometry down to 19th magnitude. So it's very, very faint.
Okay,
so it's very, very faint.
In the brighter limit?
It's brighter limit, so up to 10, I would say up to 10, it's more or less okay, but it depends on the field of view. So once we tried to do photometry on Aberration, Aberration is the famous Aberration type star, so the prototype. It's also very bright, so something like 7 and 8 magnitude brightness, and it also over dominates its field of view, which means that this was the first case when we played with it a few months ago, where we figured out that this type of naively do the convolution and you don't care and press the enter and everything is done is not the ideal case. Because when you do photometry on an 18th magnitude star or 17th or something, and your field of view is dominated by non-variable stars, which is 12, 13, 14 magnitude, then everything works. Everything just works as it should. But in the case when your star is much more brighter, like in the case of these AI phoenixes, then it should be done in a little bit differently. So we were able to solve it quite easily in a way that you just put a mask on the star. Even if you put a mask, you run the same pipeline. You don't care about anything else in a way that all of the nearby stars are very nice stars in a way that this can be used to derive your convolution transformation, subtraction, and your results will be okay. But at this moment, I didn't implement it in a kind of automatic way. So that's why I'm saying that with a little bit of fine tuning, I think it can be done. But if the star is too bright, then probably the gain of this method is not so high. So the gain of the method is when your star is fainter. So the ideal case is everything below 10, 12 magnitude. So this is a fainter regime. For the brighter regime, it's comparable. It's roughly the same.
Okay, and I'm not an expert of photometry, but maybe doing something like a PSF photometry can be helpful.
Good question. PSF photometry is good in a case when you have
crowded field, for example, no?
You have crowded field, but you are able to derive the PSF itself with isolated either isolated stars, or you have some sort of good analytical model for your PSF. And in the case of TESS, it can be done theoretically, but it is more. So the problem here is that when you do differential analysis, it's a pure linear process. If you do PSF fitting, it's non-linear process because in some cases, when you want to derive the position and the brightness, your fitting algorithm wouldn't converge. And the higher number of stars you have, and the more confused of the field of view, the likeliness of this kind of non-converging cases or case is higher. So then in the case of TESS, so the problem with TESS, there are more stars than pixels. So this is the problem here. That if you query GAIA DR2 down to 1920 magnitude on a moderate galactic latitude, you will find that there are more stars than pixels. Then how would you do the modeling if you cannot model because you have less number of equations, but your number of parameters are? So this is the problem. And for a single star, you have not just a single parameter that, okay, this is a star, but you have at least three parameters. So the centroid position and the brightness, which means that your problem will be overfitted. So this is also a problem. So just think about, just let me show you again this, the slide of this presentation, just a moment. So one of the first slides. Share screen. Yes. Yeah, here. So here you have something like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 something pixels in total. But if you check your image, there are 1, 2, 3, 4, 5, 6, 7, 8 something stars. So the number of pixels are comparable to number of stars with useful information. So how would you do the PSF fitting if you don't have the sufficient or enough sufficient amount of equations? So this is a problem. If you do image subtraction or differential method analysis, it means that you don't know the PSF, of course, but you know that the PSF varies or the PSF behaves almost the same for all of the stars. So this is the idea behind, because you don't know what is the PSF, but you know two things. The first, the PSF is roughly the same for the stars, and the PSF, the variation in the PSF is roughly the same of the star for all of the stars, which means that you just have to derive just these few numbers which characterize the difference in the PSF, which can be described with this convolution equation, where you have, say, 9 quantities or 25 quantities, depending on your size, on your kernel size. And of course, if you have thousands of pixels, you can easily do the fit. But if you have thousands of pixels and you have several hundreds of stars, like in this image, but we can see here, like this one. So number of stars are basically comparable to number of pixels, and you cannot do this type of analysis. So this is the problem with TESS, that with TESS you certainly need to try and certainly need to gain some experience or some sort of additional you need to try other type of algorithms. And of course, this is for the faint end. For the bright end, it's okay. So that's why because of the primary goal of the TESS mission, if you just think about the primary goals, so in the case of the TESS mission, it started to, okay, let's search for transiting extrasolar planet around nearby red bright stars. So this was the primary case of TESS. But if the star is bright, it means it's isolated, so it doesn't really affected by the photometry of the nearby object, even if they are fainter. And it also means that simple pixel counting could provide you good photometry. Which means that, okay, for the primary science case, you don't really care about sophisticated algorithms because simple photon counting would just work. So this is why Ames, the NASA Ames Center, where the test pipeline, the official test photometry is done, just simply use the Kepler pipeline for this purpose. Because for the science goal, it's perfect. But for anything else, it might be a good question that how would you do? So people basically just repeat the same process for fainter stars, hoping that it's going to be okay, or trying something else. So that's why I would just put some focus on how can you try to implement something else. Okay, anything else?
Does anyone have a question or comment? If not, then thank you very much, András, for very exhaustive review of the data processing of the TESS.
Oh.
And wish you good luck in your further work.
Okay, thank you.
So, thanks a lot. Bye-bye.
Okay. Goodbye.
Thank you very much. Bye.
Bye.
Okay, bye.
Thank you. Goodbye.